For our final and last learning goal, we're going to talk about how pH can affect solubility. And we'll do that by going through a few examples here. Okay, so for example, suppose we have magnesium hydroxide solid. Okay, and we recognize here that it's in equilibrium. So we've got some solid precipitate and it's in equilibrium with its ions above solution. All right. What happens as we add H plus? Well, if you think about that, okay, the H plus, we remember, is going to react with the OH minus and make H2O. So when this reacts away with the hydroxide, that's going to be removing hydroxide. And then we recognize the equilibrium position will then have to push to the right, which means more magnesium hydroxide can dissolve. And so that means it increases its solubility. Okay. So what happens if we added more hydroxide? Well, if we add more hydroxide, it's like we're adding more product, right? And now that's going to want to shift back to the solid. So that would decrease the solubility. Okay. So as it turns out, this magnesium hydroxide has another name. It's called milk of magnesia. And it is taken as an ailment for acid reflux. Because when you drink this stuff, so it's literally like this chalky, milky stuff. And by the way, this also works the same way as Pepto-Bismol, which the active ingredient is bismuth. So now you have this precipitated kind of solid chunk sitting in your stomach. And if you have an excess of acid, an excess of stomach acid, that will react with the hydroxide, causing more of the magnesium hydroxide to dissolve, which will produce more hydroxide, which can react with more of that excess stomach acid, right? And all of that just keeps going round and round and round until you run out of this milk of magnesia. And thus you will have cured your stomach acid. Pretty cool. And Pepto-Bismol works the same way. Okay, so now what about silver phosphate? So what happens when we add H plus? Well, if we think about it, okay, H plus is not going to react with silver, but will it react with phosphate? And the answer is yes. The H plus will react with the phosphate because phosphate is a conjugate base, so it wants to react with an acid. So we will say that is an increase. Okay, lovely. What about hydroxide? Okay. Well, here's where now we have to start thinking about competitive precipitation. And so for this one, I will say maybe, because it depends on how much hydroxide we have to add. And the reason for that is because now if we're adding hydroxide, the hydroxide is going to react with the silver. It's going to cause more silver to precipitate as silver hydroxide, which will in turn cause more silver phosphate to precipitate. But that only depends on how much hydroxide we add. Okay. So now what about the silver chloride? Will H plus react with the chlorine or the chloride? Nope. No change. Because chloride is the conjugate base of a strong acid, so that chloride wants to stay completely disassociated. And same with the hydroxide, we'll say maybe, perhaps, it depends how much we add. But one general rule that we can come up with is in the solid MX, if X minus is a conjugate base of a weak acid, then the solid will have a higher solubility in acidic solution. Okay, because that H plus is reacting with the conjugate base. And so excellent examples of these are acetate, oxalate, carbonate, and phosphate. okay? Because those are all conjugate bases of weak acids. So as a really cool example of this, I want to talk about stalactites and stalagmites. So for those of you that are geologists, you might find some interest in this, or perhaps you've already learned about this. But the way this goes, imagine we've got the surface, okay? So I'll say surface of Earth, and particularly areas that are rich in limestone. So in other words, calcium carbonate. Okay. So groundwater can seep through the earth, right? And eventually this can open up a vast cavern or a cave because that limestone is easily dissolved by acid, as shown by this reaction right here, right? H plus our calcium carbonate, our limestone, will dissolve that limestone into its two ions, right? So where is this acid coming from? Well, it's actually coming from CO2 in the air that gets bubbled into that groundwater. It can make the groundwater acidic via this reaction. So we'll say acidify groundwater. And if we wait millions and millions of years, it will open up an entire cavern. It will dissolve away that limestone. And it will also leave these stalactites on the top and stalagmites on the bottom. And the reason why it does that is because now once we've opened up this big cavern and as more and more groundwater continues to drip in, okay, so we'll say drip, 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 drip. Now in these drips, CO2 is outgassing, okay? So generally air can get taken up into water when it's kind of like rapid and turbulent and moving. But as that water starts to evaporate, for example, like it's evaporating into this cavern, now that CO2 is going to outgas. And when that CO2 outgasses, it, via Le Chartier's principle, makes less H plus. Less H plus means now more of this bicarb and calcium are going to be able to move backwards into the solid. And so what happens is we get these beautiful precipitates, and these precipitates we call stalactites. So they are precipitated calcium carbonate from where these acidified surface waters are running down into this cavern and becoming more basic as CO2 outgasses. And so we'll see them at the top of the cavern, and then we'll also see it at the bottom of the cavern as well. Just simply where now precipitate is dropping and accumulating at the bottom of those caves. So really cool, just one cool example of chemistry in Earth and what makes things, observable, okay? And so then the very last final thing I'll say, only very briefly, so we can use this idea here of solubility to actually make predictions if precipitation will occur in a quantitative way, okay? For now, you've just been doing this qualitatively. That's why we call it qualitative analysis. However, if we were analyzing your qualitative analysis in a much more exact and precise way by keeping track of how many ions you're putting in there, the concentrations and the molarities, then you can actually predict if precipitation will occur just from calculating it. We're not going to worry about that too much. That gets to be a little advanced and can be kind of tricky, but our same idea of this Le Chartier's principle and Q and K can apply to qual if we wanted it to. Okay, folks, that is it for chapter 16. It's a big old chapter. Make sure that you feel good about all these learning goals. And this obviously will be our entire exam too. Okay, I'll see you later.